Good day, everyone. In this video, let us discuss the section 1.1, the Schrodinger Equation from the book of Griffiths, entitled Introduction to Quantum Mechanics, third edition. We will provide the difference between classical mechanics and quantum mechanics, and after that, we will derive the Schrodinger equation. Okay, in classical mechanics, if we have a particle having a mass of m applied by an external force, meaning if we have the net external force, then we are very sure that this particle travels and it has the displacement. It provides change in position because we have the initial position of that particle and we have the final position with time. So therefore, displacement can be calculated, which means that in classical mechanics, if you know the particle's position in this initial, we can always predict the next position of that particle if we have that force applied to that particle. Now, if we can provide the displacement of that particle, then we can also provide the velocity as the description of that particle and also the acceleration. In other words, we can trace the particle's location always. The question is how to provide the displacement, the velocity, acceleration. The answer is we use the Newton's laws of motion, the second law of Newton. Second law is equal to force is equal to mass times the acceleration, where this force is the net external force applied to this particle, which means that if you know this force, substitute it here, then we can provide the acceleration. Newton's law can be applied, can be used to calculate the descriptive quantities because we know the initial position of particle. We are very sure that the particle is at that point. Now, if you know the particle, then we can predict, and that is by the use of second law. So this second law is in terms of acceleration. But remember, acceleration is dv over dt, which means that second law can be expressed in terms of velocity. But remember that the mass times velocity is momentum, which means that the second law can be expressed in terms of momentum. And this result means that the force is the change in momentum per time interval. For every change in momentum, and remember, momentum carries velocity. So if it is traveling with a changing velocity, then you have the changing momentum. So these are the variation of the second law at different variability. And we can always use this to describe the motion of particle in classical mechanics. Okay? So notice that this is a differential equation. Now in our calculus, if we have the differential equation, we can provide a solution of that differential equation. And that solution is the description of that particle. For example, we have the conservative force. When we say conservative, we don't have external forces. The force is coming from itself. So like gravity. So in this case, if we have this conservative force, then generally the conservative force is equal to the negative change or the derivative of the potential energy V with respect to the position. Take note, not with respect to time, because potential energy depends on its position. Okay, so which means that if we substitute this to the second of Newton, either of that relationship, then we come up with this one. So this is again a differential equation. Good to us because we can solve this. This is a differential equation, then we can provide a solution of that. Okay, so if we are given the potential energy, for example, of the given condition of that problem, then we can always provide the velocity. We can express that velocity in terms of the potential energy. So in other words, we can solve for we can express that in terms of position by taking the second order derivative of that position. Take note, it is acceleration. Okay? So either of the two, we can provide a description. So if you use this one, we can solve for the position, we can solve for the velocity, we can solve for the momentum, acceleration, kinetic energy, total energy, and so on and so forth. Which means that we can provide description of that particle in classical mechanics. Why? Because we have the Newton's law. The Newton's law is applicable because we know the condition of that particle, the position of that particle initially. And we can always predict that particle at any time. Okay, now the question is, what will happen if we have a particle which we don't know the location, we don't know the position? Like, what will happen if the particle is microscopic, atomic level, or atomic particle, or it can be a molecular level, or a unique particle? The question is, can we locate the initial point of that specific particle? The answer is no. We don't have the idea of which particle is located at that point. We don't know the particle. All we know is in a quantum system, we have a lot of particle, but we don't know the exact location of them. So the question is, can we apply or can we use the Newton's law of motion? The answer is no. Because ang Newton's law of motion can be applied if the particle is determined. We know the initial position of that. Now, in this case, atomic, we don't know which particle is which. It can be this particle, one, then at certain time, we don't know associate. After that, we don't know. We don't have information about that particle. So, in other words, the second law will collapse in atomic level in a very, very small particle. Which means if we cannot see the particle, then Newton's law is not applicable. Okay? So, in quantum mechanics, what will be the counter? If we cannot use the Newton's law, how can we describe the particle? The answer is we use Schrodinger equation, which is negative or h bar partial psi over t is equal to negative h bar over 2 it's bar square over 2m second order derivative of the wave with respect to x added by the potential energy times psi. This is Schrodinger equation, which means that this is the analogy to uh, Newton's law. If we cannot use the Newton's law because this is microscopic particle, then we can use the Schrodinger equation. So since the atomic particle don't have the definite position because we don't know which is which, then the only thing to describe is by calculating the wave function in the Schrodinger equation. Meaning, take note, this is a differential equation. So for all differential equation, it has the solution. And the solution of this is called as the wave function. The sign is the wave function. Okay? Which means that if we solve this differential equation, which is the Schrodinger equation, then we can calculate the wave function psi. That is by mathematics. Okay? Now, why we need the wave function? We badly need the wave function in quantum mechanics. Why? Because if we take the absolute square of this psi, we call this as probability density. If we cannot provide the description of one particle to another position of that particle, because we cannot find the definite position of that particle, then the only thing to describe this particle is to have the probability. The probability of having that particle. We know the particles are located at that quantum system. But we don't know the location of that. So the only thing that we can provide description is probability. Okay? And take note the probability has the greatest number of probability is 1, meaning 100%. So if we have zero point 0.5 probability, then we have 50% probable of having that particle. So in other words, probability played an important role in the description. And that probability can be calculated if we have the wave function. And that wave function is coming from the Schrodinger equation. Meaning, we badly need to solve the differential equation, which is the Schrodinger equation, in order to provide the wave function. So, if we have the wave function, take the absolute square of that, because the absolute square is probability density. Okay? Now, if we have the probability density, then we can integrate that with respect to the certain interval of position of the distance, then we can have the probability. Okay? Now, if we have the limit from negative infinite to positive infinite, then the probability is 100%. That if we say that taking the probability from A to B, then we have a certain portion of that probability, meaning we have portion of particles that we can provide the probability of that particle. Okay? So, what else? How is that enough that we need only the probability? Of course not. We need the expectation value. The expectation value in mechanics, this is called as the mean value or the average value of the particles present per given interval. So when we say expectation value of the position, we are taking the average of the number of particles for given interval in the position of the wave. Meaning if the wave travels in one dimension, then you have a change in position there. Then we have the number of particles. And we can describe that in terms of expectation value. Okay? So if we have the expectation value position, we have the expectation value momentum. So therefore, the momentum, not exact. So if not exact, we don't know what is the particle, what is the momentum, because we don't know the exact particle. Then the only thing is to provide the expectation value of that. Okay? And we can also provide expectation value of the kinetic or the energy, meaning the average energy of the particles in the quantum system, and so on and so forth. Okay? So therefore, in quantum mechanics, you need the Schrodinger equation. Then, for every quantum system, we have this potential energy just like in classical mechanics. Then after that, if we have the potential energy, we can solve for the wave function. So if we have the wave function, take the absolute square, then we have the probability density. Then probability can be calculated. And then we can proceed for the expected values. And so these are the things that we need to study in the next succeeding uh, videos. Okay. So the next question is how to derive the Schrodinger equation. If we understand that the life of quantum mechanics relied on the Schrodinger equation, but the question is where where did we get the Schrodinger equation, or how can we derive the Schrodinger equation? Okay, now to derive is we have to recall the classical mechanical wave equation because the Schrodinger equation is patterned in the mechanical wave equation. And take note that the Schrodinger equation is the quantum mechanical wave equation, which means that the analogy of the mechanical wave equation is Schrodinger equation, which means that the Schrodinger equation is a quantum mechanical equation. Okay? So what is the meaning of classical wave equation? All mechanical waves will satisfy the equation. Meaning, all wave functions in classical mechanics always obey the classical wave equation. Meaning, if we have the partial square of the position or the disturbance of that wave with respect to the position, always equal to 1 over b squared times the second order derivative of that disturbance y with respect to time squared. Okay? So therefore, any wave function that satisfies the condition of the wave function always called as the wave function. So function that will not satisfy the wave equation cannot be called as the wave function of the mechanical wave equation. Okay? So for example, if we have this, by the way, change this to y now. In classical mechanics, we use y. In quantum mechanics, we use v. So this is a typological error. So let this be equal to y. So we have this wave function as superposition of two waves, cosine and sine. So this is a wave. Now, this wave function can be called as a wave function if satisfies the condition of the wave. So what are the requirements? What are the requirements of this wave function? Okay. Now, take note that this k should be 2 pi over lambda. Okay. And this omega should be, which is the angular frequency, is 2 pi times frequency. Okay. Then the velocity of the, or the speed of the wave should be the product of the frequency times the wavelength. Okay. So therefore, in order to provide, in order for the wave function to become a wave function of the wave mechanical wave equation, then there's some requirements to that. Okay. So what is the relationship between the angular frequency, which is W, towards the uh, wave number, okay, towards the wave number, okay. So therefore, we can answer that if we take the derivative of this with respect to position twice, so that we can provide this one, then take the derivative of this function with respect to time twice in order to replace this, then simplify. And the result is the relationship between the angular frequency and the wave number. Okay? So do it. Take the derivative, but again, change this to y. Take the derivative of the y with respect to position. This is the first derivative. Remember, the dependence is x, which means that the second term of the angle should be constant, treated as constant, so become zero. So we have, that's why we have the key here. So therefore, this is the first order derivative, the second order derivative. Okay? So this is now the second order derivative of y. So therefore, this is it. We can replace this later on. Okay. Now, we need this one. The second order derivative of the position or the y with respect to time. So differentiate twice. So always remember that the dependence is time, which means that the first term here in the angles are treated to be constant, to become zero, because the derivative of constant is zero. So derivative of this with respect to time, this is the result. That's why we have come up this with omega, the first term. Then differentiate again. So we have the second order derivative of that position or that wave with respect to time squared. So we come up with this result. Omega squared, and we notice k squared because this is position dependent and this is time dependent. Okay, so we are now ready to substitute this second order derivative, the position, and substitute the second order derivative of time, then this will be the result. Okay, again, this is the second order derivative of the position or the y with respect to x, and this is the second order derivative of the with respect to time. So this 1 over b squared is, this is it. Okay? So then arrange. Okay. Remove the grouping symbol, then arrange it. So this is common. Take note, this is common factor, negative omega, then put it outside the grouping symbol. T squared negative is also common. So what we have now is we have A, this one, cosine omega t minus omega t, B sine kx minus omega t. Take note, this is our wave function, meaning this is actually the wave function. And also with this one, this is the wave function, meaning we can cancel this out actually. Okay? So we can remove that. What is left is we have the negative and negative becomes plus. So the resulting equation now becomes k squared over omega squared over v squared. K squared is equal to omega squared over v squared. V is the velocity of the wave. Omega is the angular frequency. K is the propagation number. Meaning if we take the cross product or take the square root both sides, we come up with this result, angular product. So this means to say that this is the relationship between the omega or the angular frequency times the wave number. It is directly proportional. So any wave function presented should satisfy this condition. Because if it satisfies this condition, meaning it satisfies the wave equation. So all function that has this relationship is called as the wave function, mechanical wave equation, because it satisfies the mechanical wave equation. Okay? Take note, in classical mechanics, the angular frequency is directly proportional to that. Which means that if you know that it is a wave function, then we can pick up these parameters and we can describe the wave. Vice versa, if you have the values of propagation number, angular frequency, then we can derive the function, vice versa. So in that case, we are describing the wave function. This is all about classical mechanics, meaning determine. The particle is determined here. Okay? Now, what will happen? What is the equivalent equation para sa quantum mechanical version? What is the equivalent mechanical wave equation for quantum level? Okay? Now, remember that the total energy should be the sum of the kinetic energy and potential energy. That's the rule. Yeah? Adding the kinetic energy with the potential energy, the result is a total energy. Okay? Now, if we think of a system that don't have the external force that interfere the particles, then we say that the potential energy is zero. Now, in that case, we call it as a free particle. So, therefore, the energy, total energy is just equal to kinetic energy. Okay? So, because this is zero. Now, what is kinetic energy? Kinetic energy is 1/2 mv squared by definition. Okay? Now we can relate this in terms of momentum by multiplying m squared over m squared, rationalizing, or m over m. So meaning if we have m over m, this will become m squared over m. So meaning 2m. So therefore, this is equal to momentum because m times b is momentum squared. So meaning p squared over 2m. So this is the energy in terms of what? Of momentum in a free space because we replace this we think of a free particle. So therefore, this is a definition of energy. Okay. Now remember that in quantum level, the energy is also equivalent to the product of the Planck's constant times the frequency of that particle, of that wave. Okay? Take note that the duality of light, we have the uh, particle description of the light, and it has also the wave property of light. Now, if it is true with light, according to De Broglie, it is true to all particles, meaning there are always two ways. It can be a particle, it can be a wave. So if we analyze that in a wave, then energy is equal to h bar times or h the Planck's constant times the frequency. Okay, so this is the energy that uh, we use in photoelectric effect, no? But it is true to all. Meaning this is the frequency of any particle times the Planck's constant. Okay. Now, if we multiply this both sides by 2 pi over 2 pi, we are now engaging the 2 pi in order to come up with another parameter. Now, the purpose why we use 2 pi, because of this 2 pi f. Now, this 2 pi f, we all know that this is angular frequency. So, therefore, the angular frequency is equal to times h bar, h over 2 pi, we call it as energy. Now, to avoid carrying this 2 pi always, the h over 2 pi is called as h bar. So, h bar is present in this equation because for simplicity purposes. So, if we have h bar, think of h over 2 pi, such that this one is h bar times omega, or the angular frequency, which means that the energy also can be defined as h bar omega. Okay? Now, according to De Broglie, that the momentum is equal to Planck's constant divided by the wavelength. Okay? So this is by definition. Now, if we multiply again by 2 pi over 2 pi, then we engage now again another quantity. Okay? Transforming this one, we have h over 2 pi and 2 pi over lambda. The 2 pi over lambda, remember, is wave number. This is k, and this is h bar, which means that the momentum, okay, in a wave description is defined as the h bar times the propagation number. Remember, h bar is Planck's constant over 2 pi. Okay, so therefore, we have the definition of momentum in quantum system, and we have this definition of energy in quantum system. Now substitute this everything in equation 1, and we have this result. Okay? So instead of having energy E, replace it with h bar omega. And take note that P is h bar K. So we can replace here h bar K, making this equation becomes what? Becomes h bar omega times h bar square times k squared over 2a. Okay, this is to announce that this is the relationship between the angular frequency and the propagation number in the quantum mechanical system or wave. So therefore, this is the relationship of the two. Take note, we have the relationship in classical mechanics. In classical mechanics, the relationship between the angular frequency and wave number are directly proportional to each other. Okay? Directly proportional. But in quantum mechanical wave, the relationship is directly proportional to the square of k. The angular frequency is directly proportional to the square of k. What does it mean? It means to say that we cannot use the classical mechanical wave in quantum system. Okay? Take note that the requirement of the classical system, a function can be called as wave function if it satisfies this condition. In other word, it can be, it is the family of the solutions of the mechanical wave equation. But in a quantum system, macroscopic, microscopic particle, the relationship is directly proportional to the square of the propagation number or the wave number. So in other words, we need another we need another wave equation for quantum mechanical system. So the question is, what is that? Okay, and that is what we are looking for. But take note, the requirement is H bar omega is equal to H bar squared times k squared over 2m. Okay? So the derivation of the mechanical wave equation, quantum mechanical wave equation, which is the Schrodinger equation, should satisfy this relationship. So this is our control point in deriving the equation. Okay? So let's have this control point, the relationship of the angular frequency and the wave number. Okay, now take note that k is still the 2 pi over lambda. This is generic formula. And also the angular frequency is 2 pi f. Okay, then if we have the wave function as again combination of cosine and sine, if you are telling me that this is the wave function in mechanical, okay, in quantum mechanical, then it should satisfy this condition. So what is that? What is that equation? So let's start with this. Okay, now if we differentiate this with respect to the position, again, this is the result. This is the same as we did previously. Taking the second order derivative becomes negative k squared a cosine minus k squared b sine. Okay, so take note that we have the presence of k squared here. We are deriving, diba? So we are deriving. So remember here is this is k squared. So if we want the equation in quantum mechanical, this is not enough. Okay? In order to come up with h bar k squared over 2m, the x squared should be multiplied by what? The x squared should be multiplied by h bar square over 2m. Okay? In order to produce the relationship. So in other words, in this equation, we will insert that term. But remember, it's negative. So meaning, we will insert negative h bar. But before that, uh, take the common factor. Okay, so this is now a common. Take note, this is wave function. Okay, so we need to multiply here negative h bar over 2m. The purpose why we do it because this result is already this one. So since we multiply the negative h bar over 2m, do it in the opposite side to remain the sign of equality. So multiplying this one, this will become positive h bar square k squared over 2m, and this is now the relationship that we want to. So therefore, we have this result. Okay? So again, this is psi. This is our wave function. So replace that with psi. What is this result means to us? This result suggests that one side of the quantum mechanical wave should have this one. This is the recommendation. Okay? Should have this should be the first one side should contain this whole factor. Okay? These expressions. Why? Because if you simplify this, you will come up with this result with the presence of h bar k squared over 2m. And this is it. This is our control point. Okay? So one side should be this one. And the other side should be h bar omega times psi. Why? Why h bar omega? Okay? So that you will come up with this result. Okay? Now, the question is how to produce h bar omega psi. Now, if you notice previously, if you take the derivative of psi with respect to t, it will come up with this relation. Okay? So, in other words, if this must be the one side of the quantum mechanical wave equation, then the other side should resolve to this one. Okay? In order to produce its bar omega. So, what is that? Expression that can provide this one. Okay? So the tentative quantum mechanical equation should look like this. So this is now our one side, and the other side should be the derivative of the wave function with respect to time. Why is it that we have this one? Why is it that we don't have angular frequency? Remember, we need angular frequency here. Why is it that we have the derivative rather than this one? The answer is, if you take derivative this wave function, look at this one, with respect to the time, it come up with omega. Okay? So therefore, that is what we are looking for. So if you take derivative of this, we understand that we can produce angular frequency, first order or first degree. Okay? So with that, we can have this value. So in other words, this is our tentative. Tentative, why? Because we have the presence of C. What is that C? That C is called as a Fuchs number. Okay? It is a constant value called as Fuchs number to make sure that everything becomes okay. What does it mean? In a quantum system, we have the interfering uh, uh, forces or interfering factors outside. So in order to take care of everything, or in order to remain this a sign of equality, then C should be identified. And what is that Pugh's number equal to? So the next move now is to solve for C. Now what is C? So solving for C, okay, solving for C is we can do it by what? By substituting the value of this one, the second order derivative of the wave function with respect to position, and substitute the first order derivative of the wave function with respect to time. And this is it. This is this is what we did previously. The second order derivative of the psi, and this is the first order derivative of the psi with respect to time. This is with respect to the position. So therefore, substitute it here. Okay. Then next is, of course, remove the grouping symbol. This will become negative. It's bar okay. So negative negative becomes plus. So this is it. No? And we have this result because we have omega here. So therefore, that's it. No? So this is CH bar omega. Now remember that this is our relationship. Diba? H bar square k squared over 2m is equal to H bar omega. So meaning we can cancel this out. This is equivalent to what? Because they are equal. This is our condition in quantum mechanics, quantum mechanical system. So meaning we can cancel it out because they are equal. So leave it out of the expression. So meaning we come up with this result. And remember we have C. So distribute the C. Then we can notice we have two terms in the left side and we have two terms in the right side. Each term here contains cosine and we have sine. Also, in the other opposite, we have sine and cosine. Now, in mathematics, their corresponding trigonometric function must be the same. Meaning, if this is true, then cosine term is always equal to the corresponding cosine. And this sine is also equal to that. If it is true, then this is also true. Sine equality. Which means that we can split this into equations. Cosine, A cosine kx omega t is equal to negative CB cosine. Okay? So, we have this first condition. And the other condition is the corresponding sine function. Okay? The purpose of this is to solve for C. Can we solve for C? Of course, yes. Take note that this will be cancelled out. So, leaving this as A is equal to negative CB. While this one, sine function, expression can be cancelled out also. Leaving this B is equal to CE. So therefore, take note that we can solve for C by substituting C. We can we can solve for C here by substituting B equal to CE or vice versa. Okay? So therefore, if you do it, combining these two equations, replacing B with CE, so this will become A negative is equal to negative C times B, but instead of B, CE. So therefore, simplify, we come up C is equal to I. Okay? Why? Because dividing both sides by A becomes 1, C squared negative So meaning square root of negative 1 is imaginary. In other words, C is equal to I. So in that result, we derive the Schrodinger equation for a free particle because take note, we equate B is equal to 0. So the Schrodinger equation in a free particle, substituting the C here, which is equal to I, is negative h bar over 2m partial square of the psi with respect to x is equal to h bar partial psi with respect to time. Now, what will happen if we have the potential energy other than zero? Meaning, if it's not a free particle, what is the equivalent? Schrodinger equation. Of course, very easy. Just add the term here. Take note. This is position dependent. So therefore, this is just equal to V times psi. So this is now the Schrodinger, the general form of the Schrodinger equation for a non-free particle. Negative h bar over 2m, partial square of psi with respect to the x is equal to b psi is equal to I h bar partial psi with respect to time. Okay, so thank you for listening. See you in my next video to 1.2.